All right, so great pleasure to introduce Facundo Memoli from Ohio State, who will be talking to us today on hierarchical clustering methods for asymmetric networks.
Thanks, Peter. So this work that is joined with Gunnar Carlson, Alejandro Santiago Segarra, they are from UN. So, explain what a network is for the context of this. Network is N consists of two elements, a set of nodes, finite set X, the function A sub X, which is a function of X into non-negatives, which are dissimilarities, and we make the assumption that the between two nodes, X prime is 0 if the two nodes are identical. There's no assumption about symmetry, so the definition encompasses also finite metric spaces. So on the right, you see an example of a network and also the way we tend to present or draw them. The weights associated to an edge are drawn above the edge. It will be a collection of all networks. I'm referring to that notation quite a bit. Concepts about clustering. So traditional or flat or star clustering assign to a dataset a partition of the nodes. So what we understand as a hierarchical clustering is the assignment of a nested collection of partitions to a given dataset. And nested partitions is usually called a dendrogram. So for example, we have a set X with nodes B and C. So the way you represent a dendrogram on the x-axis, you have a parameter that tracks a dendrogram at value 1 will give you a partition into singletons. So if you have a vertical line to the value, the scale value 1, you get 3 branches and see that they correspond to the individual nodes. So 3, when you see that it corresponds to the singleton node A, when you see that corresponds to the pair AB. So now we are then put into the same block of the partition D of 3, and sometimes for D of 5. Only now at the value 5 have coalesced into the partition. So normal definition for this, so we say that dendrogram is the following. So if X is a finite set, P of X is a collection of all partitions over X is a right continuous monotonic function dx from the negative reals into partitions of X, and here we take to the refinement order on partitions. 0 gives you the partition into singletons, and something like this scale is a scale T0 program gives you the output, gives us an output the partition into only one block. So D, the collection of all pairs X dx, where X and D sub X is a dendrogram over X. We write what the hierarchical clustering methods. A cluster will be a map from or collection of all networks into the collection of all dendrograms D, with a property that the underlying sets. So if you have a network XX, then you send that to a pair X dx, where D is a dendrogram or X. If there are any questions, but this is going to be the base construction for next. Dendrograms are useful for visualization, but they're not so useful for prove some technical properties of the method. So we represent dendrograms as something called metrics. So metric is which satisfies something called a strong inequality. And given a dendrogram, here, you want to each pair of nodes in the value of the scale parameter so that the two nodes have of the partition at delta. So ln delta to x prime that x are in the same block of the partition d of delta. The minimum delta so that this happens, and that's a value assigned to the pair x and x prime. Now, working with partitions, because of the definition of dendrogram, which is a hierarchical family of partitions, we can strong triangle inequality will be satisfied. And we read clustering from collectors into the collection of all finite ultrametric spaces with a property that these maps respect line sets. So we will to a representation of hierarchical methods. Let's look at the symmetric network. So AX is symmetric if on AX the disparity function satisfies symmetry. Think of AX as a matrix, well, you require that the matrix be symmetric. So very well known method that applies to symmetric networks, which is called hierarchical clustering method. So I'm going to tell what the method does. I'm going to use this representation or this formulation of hierarchical clustering, which define for every network X, AX, ultrametric X, symmetric US, produced by the single linkage hierarchical clustering following. You consider nodes X and X and all the sequences of at X, then going to some X2, etc., and that for some Xn, the final point in the sequence, you reach time. For chain, C of the maximum between any two consecutive nodes. So that's it in blue right now. The number to every chain connected is optimized, minimize over all the chains X to X prime. So that one can define ultrametric UX on X, and this is a known or maximal subdominant ultrametric, and UX is a pointwise sense ultrametric which is bounded above by AX, the given dissimilarity.
Sorry. Sorry, can you explain that in more detail? Like, what does subdominant mean, and what point was the maximal mean?
That means that this inequality is true for of X cross X. All that satisfies this inequality is the maximal one. But it's just one property by people know this ultrametric. One can prove that would be true. So you can apply to sim networks. We aim to characterize methods by properties or axioms on them. So, describe that we adopted Now, this is inspired by some work by Kleinberg, the 2002 paper in NIPS. The context of the paper by Kleinberg was standard method. That to assign a single partition to a matrix space. The that are that either exists no good method. He proves a theorem for classes that satisfy certain axioms. In 2008, we were thinking maybe if we read axioms, some of Kleinberg's axioms, in the kind of hierarchical method, then we can move the immutability theorem, and that led to axioms that I'm going to check. So the first one is the axiom of value. So method H from N satisfies the axiom of value if it is prescribed on of two nodes. Of two nodes looks like this. P and Q weights alpha and beta. Now that H all learns the form that is of alpha and beta. Okay, will be the partition. The part coded by the dendron will be single to partition from 0 to of the two varieties, and onwards it will be the partition into one block. We also considered axiom of translation. The following. So suppose that you had two networks, y, and so I have a map phi from the set at y with that these the polarities. So that's true. Yes, for the output of applying your method to X, and right for the ultrametric coming out to Y. So we satisfy the axiom of transformation if that non-increasing. Okay, the following in an example. So suppose I have this X with three nodes, and the similarities that are shown on top of the edges here. I have a network with three nodes, Y1, Y2, and Y3, where polarities edges, corresponding edges. So there's a natural map here, which is the one down to Y1, X2 to Y2, X3 to Y3. So that turns to be polarity non-increasing in the sense that size inequality for first of nodes Xi and Xj. What we require is that if we co-clustered in the into X at some value delta, now the two nodes via the map phi also need to be co-clustered at value delta in target Y. Function, if we were talking about this in categorical terms, so we call them again the similarity non-increasing maps. So H is admissible when the two axioms are satisfied. That is, that them has a prescribed behavior on networks with two nodes and vice this function. Well, that satisfies both axioms. We call it reciprocal clustering, H super R. Taking network X, AX, and write output as X, UX, R. Now, it does the following. So, method which encourages hierarchical clustering that is applicable to symmetric networks. So, they also take your network, which may be asymmetric, XX, and slice it in this. Okay, that you will take between point 1 between and the transpose of A. So that works. So then you can apply single linkage to that. Method H super R. Now, when you verify that this method satisfies the. So the method is telling you is that if you want to co-class X and X prime at some delta, then you'll be able to walk from X to X prime by some chain of nodes, X0 up XL plus 1. So the dissimilarities in the two directions are bounded by delta. All of them need to be bounded by delta. So there's bidirectionality by this symmetrization. In an extreme of all methods, another example called non-reciprocal clustering. So reciprocal clustering does something slightly different, or different if you wish. Here, for reciprocal clustering, we are first symmetrizing single linkage. Okay, so in single linkage, you take some dissimilarity function, this one, the symmetrized, then you look at maximal jump between any two consecutive nodes on a certain chain, and then you minimize over possible chains. For reciprocal clustering, we essentially take the opposite order of those two operations. We first X to connect X to X prime, we chain joining X to X prime, then I'll jump between nodes in the chain, and then minimize over the choice of lane C join prime. The same concept to a chain in the opposite direction, a chain that goes from X prime into X. Tries by taking the maximum between these two. That, as it turns out, induce an ultrametric over X, which we call UX and R for non-reciprocal. So, admissible. One observation, and go back to the reciprocal method. So suppose that you're given a symmetric network with disparity AX. These two values, this one will be when you this minimum, you same value A of xi to xi plus 1. So in fact, the reciprocal hierarchical clustering reduces to single linkage. Now, then also that for reciprocal clustering on a symmetric network boils down to double linkage to the same network. So networks both reciprocal are identifying single linkage, and by they however differ on networks. There's a third method, which is a whole family of methods, which are semi-reciprocal methods. So for reciprocal methods, we do the following. some positive integer t bounded by 2, and we compute a new dissimilarity, ax, your original dissimilarity, and we change that dissimilarity by some following. So here, C sub t means the collection of all chains join prime, but with length at most t. Then or a construction similar to the one of according to single linkage that I showed for the constraint chains. We look at the one between any two consecutive points on that chain, minimize over the chains with a t point. Now, done this, we factorize this dissimilarity by taking the maximum A SR of t and transpose. That gives this block in blue single linkage to that. An observation that if t be infinity, if you strain on the length of the chain, that uses a non-reciprocal method. So you essentially take a very long chain to go from x to x prime. If to E2, then do the reciprocal method. So look at matching that you can and come back. Then this picture here. So then local methods with parameter t interpolate between reciprocal and non-reciprocal methods. So you can receive methods by restricting t to E2 and using the non-local method by formally letting t be infinity. Now, and by the way, so this.
So no, can I just interrupt you?
Yeah.
Why is the reciprocal case t equals 2 and not t equals 1?
Well, where is it?
Case you take the cost of going for each pair.
Right. I think right. Yes. So in here, because now I'm using t0, sorry, x sub 0, right? I'm using x0 to be the first one, and then x1. Yeah, 1. Sorry. With the assumption that I'm representing chains as start at x0 and then x1. Yeah. So says that these methods, the H, S, R of T, they are all admissible as well. Now, we have following results. Suppose that you have method H that satisfies dimension. AX and by UX, the geometric applying A to your work X. So then equality takes place. Value as an X prime, the old value associated by the reciprocal method to X and X prime, and bounded by that of non-reciprocal method to the points X and X prime. So that no admissible method is the rows by reciprocal. And in part, you restrict the method to symmetric networks, since non-reciprocal networks coincide on networks and coincide with single linkage, you obtain networks. The only possible method is single linkage. Of a result that Gunnar in 2008. In this method, HT, the semi-reciprocal, that of intermediate methods, that is, methods that are contained in between the and the non-reciprocal methods. Couple more I wanted to say is that we have other families of methods that live between non-reciprocal and reciprocal methods. So far, enumerated 4 infinite families of methods that live between reciprocal and non-reciprocal. So we like that because for symmetric networks was that we had 2 very simple axioms, 2 very simple properties, then established that there was a unique method satisfying both. Now move the symmetry, very wild environment. Both methods seem to satisfy the axioms that were reigning, very restrictive before. Now that is enough for pinning down exactly the that are admissible. Came up is, well, why don't we try to impose some axioms that might use, and that, by the way, should be inspired on, say, engaged in observations that people or concerns that people have about good practice. Why don't we take some of those properties and we try to impose them or our admissibles and try to narrow down the all possible methods. Going to say that next, and then suppose that you have methods for each satisfying selection of axioms. Okay. Further, or understand whether the method is also stable in some sense. Important, say, it does be in that the methods have to be stable. So we also have stability as a separate property of methods. So this is one family of methods that is different family, but which is the method is itself very simple to describe. So suppose that you have any 2 admissible methods, an H2. Now it's between 0 and 1, and I'm going to the construction of a interpolating method H sub theta. Interpolate between H and H2 value of theta. So take any network A sub x, considering your methods H1 and H2 to the network. So you will another x1 and x2. A new dissimilarity x, and that similarity is very simple. So you just take the convex linear combination of the 2 ultrametrics and use it for each pair of points. So that is AX super 1, 2 of theta. Now, because ultrametrics and meta are symmetric, symmetry will be symmetric. So then into the context of symmetric methods, so the natural and actually only choice here is to apply single linkage if an admissible method. So we made this convex elimination with single linkage in geometric UX12 that depends on theta. And let theta be one of the two extreme values, 0 or 1, you will recover either H1 or H2. And this defines an admissible method. Strength of a method, I mean, it should be, we're done, what are the properties that this method does avoid? And there's one clear property, and that is the property invariant to scale. So we were looking at the following property. Suppose I have a function C, positive reals, that 0 is 0. The idea that A being a clustering method, which in this case we understand as a maps into all three, with relativity between C and A for all these. Now, be this convex linear method satisfies this. You can read things up so that this elimination destroys the commutativity for some functions of C. So the method, the non method, and same a reciprocal family, they're all scaling invariant. We're thinning out the post-admissible methods now if we impose additional constraint that the methods be invariant. Now, as a way of giving an indication for scaling invariance, well, this means that essentially the result obtained when you apply a method should depend on the units that you measurements on. Okay, so it's before should be the same as applying clustering and then changing the units. Now, recently we had two other axioms or properties of methods, and I plan to talk about only one of them. But then, so one property that was interesting is some sort of locality, that is excessiveness. So Gunnar, we look at this property in the context of finite metric spaces about 3 years ago, and it was a reasonable property for trying to capture some behavior of flat methods. This means, let me pick a tenderum. If you apply your message to some network, say this one, and this tenderum. So suppose with some scale value, this can, and the in cluster or induced blocks in the partition dx delta. Now the blocks for x1, one block induced by the choice of delta prime here, and your original metric to that block x1 and x2. A new network, a subnetwork, original network. Now your method again, but now to this subnetwork. This excisive is that if that result is identical to the restriction to the subwork. So that's local consistency. The other that looked at is something that may have to represent the method in a metric way, and we got represented. Really suggesting for methods with typical clustering. So let me intuit provide a definition for what these motivic methods do. Suppose you have some network that's represented by this in the gray area nodes, and there is line to these two nodes. So we interpret cost as the value of the ultrametric at these two. The following. So we have some the motif that try to place that we can node into the other in some sort of optimal way. So we create a path by replicating the motif on the environment. And when I say replicate the motif, it means that you distort the motif a little bit so that it fits in your environment. And every distorted, you pay a certain amount. Now, you're optimal if the maximal distortion is minimized. That is the idea for a motif class. Let me try to get in the context of the reciprocal method. So remind you what the reciprocal method did. The reciprocal clustering method, we prime where delta equivalent or co-class at some resolution or scale delta, if a bidirectional path between x prime, so that the weight or similarities in consecutive points by delta. So these are that to find at some resolution level delta. One can view that description of the clustering method as civic in the following way. So our is going to this circle sub 2, which is a network with only two nodes, on one in the directions. Now I have X, this element or the original network, and this is to underfy the cost of joining to X prime. That is, I'm trying to assign the ultrametric value to the X and X prime. So consider one given check that starts and ends at X prime. That means X0 equals X, X1, X2, X3, etc., etc., to X sub L equal to X prime. The X0 equals X and X1. Now, how I have to amplify this motif? By which constant do I have to multiply the two so that the motif is this network? And so I can find that the similarity, non-increasing map, amplify motif and spanning the two first nodes, x0 and x1. Value between x, that's how we call it the minimum function that we need, minimum function of this network that we need in this map. That x and x1 are the image of the map. Okay, this for all consecutive pairs of your network, and the maximal amongst values, delta between x and x1, delta between x1, etc., etc. And then for the choice of chain, remember that we have a certain chain joining x to x prime. Now, I go to what in the case of clustering. The question is that we could do here for motif, not just this simple one. We loop, we take a loop with 3 nodes, a loop with as many nodes. Normally, if we thought about that, if we wanted to do that as well. Now, what happens is that essentially represent equivalent conditions. So our asymmetric networks will be representable if a method is existing. Thing I to promise to do that before is that even if it's not clear that satisfy the axioms in theorem guarantee stability or not, if all admissible methods happen to be stable, we are proof that are stable. Following sense. So read the definition of hierarchical clustering methods using and the notation that H sends a network into a parametric space. So to guess stability, we the following structural representation of the chromosomes by comparing function on the division products of a node set with itself. So here two networks x with this ax and xy and ay they're all binary relations between y which are subjective. We call this given r between x y. Look at this. The of the disk in absolute value. The similarity is associated to the components and pair of points in the components. So if you plug into x and xy finite metric spaces, you recover the original of our distance, but this also makes sense for things for which satisfy triangle inequality. Now, we are talking about methods that take a network and map into finite metric spaces. So, say H is stable, there is L for which holds for pairs of networks and NY. So there should be also N should be n, is metric dn that we have. So in each happens to be a Lipschitz map between of all networks and the space of all ultrametric networks. Following, so the reciprocal method and R, the non-reciprocal method, finitely representable method. So stability by methods by extendability because of the equivalence theorem between functions. So let me do some conclusion. So to a few properties that to ask from methods on next. And those you can derive a theory range of all possible methods. So we see axiom of value and the axiom of transformation. We then families of methods, that is, methods that satisfy those two axioms. So that's a very happy situation because you're able to properly classify methods. You don't know which methods are the ones that you should be using. So then some those representativity and exclusiveness, and even though I did not have a slide for this, I did mention that representativity and exclusiveness, these two properties have balance. We established that the methods that are easy to pass motivic methods, they're local as well. So the verification theorem then for these methods which are easy to describe, we interpret that methods which are easy to describe because you have the lagging parameters, and the parameters in this setting are just some networks that you fix in these all possible clusterings of all possible networks. Something that to study is of the way you could try to implement these methods. There are some nice underlying say for all these methods got disrupted by this. There's some, where is the screen? There's an answer in the form of a diode, max diode, and many that people have been for symmetric adapted to this symmetric setting. So what we're more recently with depends on grid or classification of all methods in terms of inclusiveness or and representability. Yet have a very all non-negative methods, that is non-representable methods. There exist infinitely many though. So all that do not satisfy this locality space is infinite, and they change interesting, say, from a theoretical point of view. We to be able to gain more insight into them by putting further properties. That's all I wanted to say. So we do not hear comments while I speak, but maybe we can have a bit of a discussion.
Let's thank Facundo for this talk. Thank you very much. Questions? For your you just see the maximum of the two kind of asymmetric different distances between the point work.
Yeah.
Can you say something about the motivation for doing that? I mean, it seems to me like there's other choices you could make. You could take the average, for example.
Yeah. Well, first say that think of this, or one way of thinking of the similarity is something that tells you whether difficult it is to for one node to influence another node. I wanted first to study sort of methods that the two will be co-clustered if they influence each other. Choice suggested saying, okay, we want to take the maximum. We the implication of choosing, for example, the minimum here, and found other methods that look a bit different from that current choice of the axiom of value. So this will be an analog, say, to strong, saying that you have some strongly connected components. Will give something analogous to weakly connected components. I mean, when you just have path, require this a bidirectional path to nodes. You obtain a range of different behaviors by. Now about the average, I think probably doesn't go well with this other axiom, with the axiom of transformation. Say range of ideas seems to be rather L infinity with behavior when you take this.
Any others? So you can also tell me about the axiom of locality. I mean, you don't necessarily want that because if you have a subnetwork, there's maybe only so much you could do for clustering. But if you know something else, you necessarily use that information. Here, I guess you're picking a threshold, so you delta here, and then the picture that you have, and I got ideas that you don't x3 is too far away to influence how you want to cluster x1, x2. Is that the idea for the? This is a mess.
I'm saying that should be a property that you want. I'm saying it's a property that some methods means some consistency. I mean, you that methods are perhaps idempotent. If method twice, then things should not change. It's natural to try to impose, and because you're moving from networks into ultrametric networks. Ultrametric spaces, but ultrametric spaces are also networks. They defy, I mean, all the conditions that you need to induce a network. So to apply the method again to the output of the method itself, so you can compute h squared of some network. But idempotency is implied directly by this. One can apply those two axioms, value and transformation. Any satisfying them will be idempotent. So sort of this global consistency, applying the method to the result of applying the method doesn't buy you anything new. you're keeping in mind, then you could say, okay, what if I try to localize this condition? And that's exactly what leads to the idea of exclusiveness. You have the subnetworks induced by the method and apply the method to the subnetwork. But the thing is that it happens to be the representation. The mesa locality are exactly the methods we wanted. Now, interest in making this definition comes from the that that methods which tend to be representable can be as methods that you can describe with parameters. The parameters are just the networks that the motifs you specify, and those describe exactly what the method is going to do. Now satisfy that are complex methods. The methods are difficult to describe, and those in our interpretation that which is not local, think that the method is well, it's difficult to parameterize. Yes, but you can that we just the method. Oh, I don't know. I lost audio, and I see that you're speaking, but
sorry, I muted myself. Sorry. I started asking questions, so I can say one more thing. I think there's a nice categorical relation between a category of ultrametric spaces and a category of metric spaces, and that it's like reflects subcategory of the other. I was wondering if something similar might be true in this here. Maybe we can talk about that if you know about that.
No, I have about that. One further comment is that all these functors, so these are hierarchical clustering functors, happens because you're in symmetry. Convert a asymmetric object into symmetric. The output you're saying, I do want to have a drum. Eventually, an ultrametric, and ultrametrics are symmetric, imposing symmetry on something that was originally asymmetric. Very wild, of infinitely many admissible functors. That if you say I don't care about symmetry at the output, well, that is you to look into some sort of generalization of those. There are some generalization of ultrametrics. We just directed ultrametrics. It's something that satisfies the strong triangle inequality, but it's not symmetric. And in that setting, this I say those like uniqueness. So unsettling that on the one hand, people that we seem to be able to symmetric structures such as dendrograms better because we can understand them easily, but then that forces you to accept that a whole bunch of methods that you don't know how to describe yet. Interpret and dendrogram easily, then you know which method you have to use because you have a unique method. So
maybe we'll end there. So thank you very much, Facundo. If else is, do I clap?
Thank you.
Thank you very much.
Thanks, Peter.